3/3. And though my students, County College, liberal arts students, have had statistics when they were in middle school, most of them probably have not had it in high school, and this is their first college introduction to the course. They've gone through mean, mode, median, range, and now we look at the bigger picture. We look at those words as measures of center, and then go on to measures of spread. There is a PDF of this page, so should you wish to use it while we go over the page in the video, you're welcome to do that. I will then post the video, and it'll be linked here also. So we begin. First thing one needs to know is there are new symbols, and one of them is a capital Greek letter. It's a summation, is the name of what you're doing mathematically. You're adding up, you're summing terms or numbers. The capital S or sigma is a Greek letter, and we use the capital sigma for an operation and in an expression. And Greek letters, lowercase letters, are used for population parameters, and lowercase letters in English are used for samples. So you have the mean, which is X bar, standard deviation, which is S, population mean is mu, and this is the lowercase sigma for standard deviation. Notice that every single one of the symbols here uses that sigma. This many people know from middle school. X bar, which is the symbol for mean. The mean is the sum of all data points divided by the number of data points you have. It can be written in more detail, say start with the first and go through the nth. One might say the variance then is the sum of all the squares of the difference between the data point and the mean for every single data point. And if you're doing it for a sample, we make it n-1 on the denominator or the division. And for a population, we just use n. The standard deviation, and you'll get a better picture of what that is and what the variance is as we go through the arithmetic, but the standard deviation is the square root of the variance. The words, terms for center include average, mean, mode, median, same as in high school, same as in middle school. The spread you learned in middle school was probably the range. The range has two meanings. It's the set of all possible y values in a function, but it's also in descriptive statistics the difference between the highest and lowest pieces of data. Another spread that one might know from middle school is called the interquartile range. And in order to know what that is, you have to know what a quartile is. So we go there next. It's the median is the middle number when all the numbers in your sample are arranged from lowest to highest. The median is the middle. It's called the second quartile, the 50th percentile. If you go from the minimum to halfway, then the halfway point of that is called the first quartile, and the halfway from halfway to all the way to the end, the top number, the middle of that is called the third quartile, the 75th percentile. So the inner quartile range goes from the third quartile down to the first quartile. As a subtraction, it gives you a number. Another measure of spread is the variance, and we know that there's a relationship between the variance and standard deviation. The variance is the square of the standard deviation, but the standard deviation is the square root of the variance. We'll get to more of that in a minute. Symmetric means balanced bilaterally from left to right. And distributions are ways that the data is spread out. So let's just look at the left side, the right side first. Here we have a distribution. It's uniform. All the frequencies are the same. Here we have a bell-shaped binomial. In each of the histogram bars is balanced on the left and on the right, with the center being the highest. Here's a normal, here's a bell-shaped normal distribution. This one's discrete, this one's continuous. That's gone over on a different day. Here we have skewed. Notice in the bell shape, the mean, the mode, and the median are all in the same place. In the skewed, the mode, the most frequent score, is on the right, and the tail is on the left. It's called skewed to the left. You name it by the tail. Skewed to the right would be the tail is on the right and the mode is on the left. Bimodal, two modes, mean you don't have one mode, one most, you have two of them. J-shaped, reverse J-shaped, and chi-squared. The distribution people are most familiar with is called the normal distribution. It is bell-shaped. The mean, the mode, and the median are all right in the center in the same place. If it's a normal distribution, the standard way of putting the intervals of importance, the standard way of doing that is to call 0 the mean, mode, median. That's right in the middle. And then up above, 1 unit, and then 2 units to the right, 3 units, and down 1 unit, 2 unit, 3 units. Let's go over that in more detail. In a bell-shaped distribution, the mean is in the middle. That's the bell. That's the peak of the bell. And if it's a normal distribution, we label that mean 0. For the standard way of doing it, each distribution would have its own mean, but we're using 0 here. We're using X bar here. If it were a population, we'd put mu there. The phrase unit refers to the distance from 0 to the first interval notation. Very often it's 0 to 1. then 1 to 2, then 2 to 3. So this is the normal way of marking it. This is the mathematically accurate way of marking every single normal distribution. The nice thing about this one, it's the percent of normal distribution scores in each interval is what it's called. And the hump, the bell, the peak of the bell, these two intervals each, because it's symmetric, they have the same number, same percent of scores under the entire curve. You have to have 100% of the scores accounted for. Right in the middle here, within 1 standard deviation of the mean. That means going from 1 standard deviation below to 1 standard deviation above. That's 68% of all the scores. That's for every normal distribution. This is a formula which you do not have to know, but I'm going to show you what I'm talking about in a slightly different format. These files are downloadable. I'm going to hit this one. It takes me into a calc folder I have. And it brought me to a page that showed me a little bit of calculus here. I'm pointing out a thing called a box. This is a way of looking at the area under the curve is my goal. My goal is to find out what's the total area under the curve. And if I break the curve, the plane, partition it, cut it up, then I can add up a bunch of areas, rectangles or trapezoids, whichever is desired. In this picture, I'm just showing rectangles. And the height in each case in this picture is the height on the left, not the height on the right. This is on the left, that height, that height. We do have a picture showing the height on the right. Same idea, you add up the areas. We're going here to look at a probability distribution. That's that formula I showed you just a minute or so ago. Here's the standard normal curve showing the distribution. And if you look at the hump in the middle, the bell-shaped curve in the middle, what this is set up to do is show you the area. So if you run your area from the value of A, which is set right now at 0, to the value of B, which is set right now at 1, from 0 to 1, the area should be 34%. There it is. Let's make the area run from -1 to 1. That's the area within 1 standard deviation of the mean. That's 68%. We looked at that just a moment or so ago. These are approximate numbers. I only have 32 boxes here, and that's the accuracy I have. I can go within 2 standard deviations, and we should add 13.6, 34, 34, and 13.6. So let's go from -2. Nope, didn't do that right. -2 to 2. And there we go. 95% of all the scores in a normally distributed sample are within 2 standard deviations of the mean. And we could get fancy. Let's just go from 0 to as high as we can go. Well, we don't even have to go that high. Let's start at 0. And we'll go to 2, And there you have 49%. And let's go to 3. And that's a bit over 50% because of rounding, because of the fact that I'm not doing perfect lines, I'm doing boxes. But that's sufficient for you to get the idea of how the scores are computed. Let's just run it from -3 to 3. See what the approximation is. It's just about 100%. We don't need that anymore. So you now get the idea of a bell-shaped curve, many data points, heights, lengths, error measurement, standardized test scores. These are all normally distributed scores. They follow the percents within the interval. There's another spreadsheet I'd like to go to. But just before we go to that one, I want to go through a few more vocabulary words. Standard normal has as its mean 0, and the standard deviation is 1. That means in a normal number line, when you're doing just plain graphing, line does not have a length. Line is infinite. So there's really no such thing as the middle of the line. We put a 0 there as a center point, arbitrary. We'll call it 0. Then to the right have positives, to the left are negatives. That scale labeled here is 1 unit. That's just a plain old number line. If we look at the standard normal number line, we're going to have a center of 0, and that unit is 1. And the letter for the variable is called z. Standard normal number line, instead of using an x, we use a z. But these lines match up. Here, on a standard normal number line, the center is 0 and the scale is 1. Here on the statistical number line, the center is x bar and the scale is the standard deviation. You still don't know where it came from, but you do know the word now. That's what it's used for. It's the scale on a statistical number line is the standard deviation. The entire number line may be written in terms of the mean and the standard deviation. Here's a labeling. Here's your mean. Go 1 unit, statistical unit up. You take the mean and you add 1 standard deviation. Going 2 units up, mean plus 2 standard deviations. I think you get that idea. Again, 0 in the middle, no middle, but we fake it. Another way of looking at it. If you were to match up a normal number line, the center is 0 and the scale is 1 unit. On a statistical number line, the center is x bar, the mean, and the unit is the standard deviation. We can switch 1 unit to the other. I think we're going to skip this one for now, and we're going to look at the spreadsheet and then come back to this. So let's go to the spreadsheet. And I think I may have 1 copy open. All you have to do is click and download it. I already have mine open. And it's set to go. I opened it to the table of contents. there are plenty of other things to look at. We're going to go through this and then play with more numbers. All of this you may do at home, watching the video, whatever you wish. The goal is to play with the data and watch it compute. I think I'm going to slide, oh, the yellow self-computes, the white is where you enter your data. Don't touch the yellow boxes. If you do, just dump the whole spreadsheet and open up another one. They're free, downloadable. I'm going to go to this sample, which has 4 pieces of data in it. Rather than playing with the bigger ones, we'll go there in a minute. Okay, so my data that I happen to have sitting here, and these are in order from lowest to highest, just because I found that convenient to show you what I'm talking about, then we'll move them. So I'm going to make this a 2. Nope. Go down, make it a 2, make it a 2, make it a 2. Every single piece of data is a 2. That means their average is also a 2. And if I were to take the piece of data and subtract the mean, 2 minus 2 is 0 in every case. If I add up those mean, data minus mean, and square each of it, data minus mean, take the quantity and square it, I get zeros. If I add those up, I get 0. There's no variation. There's no difference. Everything's the same. The variance is 0. All the scores are the same. Let's make the scores a little bit different. Let's make this a -2. Make this a 0. Make this a 0. Make that a 2. Notice when you add them up, divide by 4, you get 0, so the mean is 0. -2 minus 0 is -2. Square it, you get 4. 2 minus 0 is 2. Square it, you get 4. Sum is 8. We're using 1 less than the number of scores, and the variance is the sum divided by n minus 1, 1 less than the number. And the square root of that is the standard deviation. Let's make it a little fancier. Let's put this as, make that -2, make that -1, make that 1, make that 2. Again, you can check the computation. Now the variance is 3. Let's make it a bigger difference. Let's make this -10. And let's get really hairy over here. Let's make that a 20. The average is now 2.5. If I do the arithmetic, 1 minus 2.5 is -1.5. Square each of them, add them up, take the square root. I think you get the idea of, you don't know why, but I believe you understand the computation. I'm going on to the next sheet. Again, here we have just the 4 numbers that we can change, and everything else self-computes. And now I think what we have on this one, I've labeled it a little better than here. No, the labels are the same. I've asked you to order your data this time. In other words, put the lowest number here and put the highest number here. The reason I've done that is so we can figure out some of those other range descriptors. The minimum you see is 1. The maximum is 9. 9 minus 1 is 8. That's the range. All the yellow boxes self-compute. And I'm going to remove the none. And let's change some of the data. Let's leave it in order. For the record, there are 1, 2, 3, 4, 5, 6, 7, 8, 9 pieces of data. The middle one is the 5th one. That's the median, and that's 5. Let's just change some of these. The maximum is 5. The minimum is 0. The maximum is 25. 25 minus 0 should give me a 25 right there. Highest number is 25. Lowest number is 0. The mean, according to the computation, I probably should have put a sum here, and I didn't do that. Let's just do it now. I'm going to add up these numbers. I got 95. Now let's just turn it yellow. So when you add up those numbers, you get a 95. 95 divided by 8 is 13.33. And that's the average. The formulas, as we looked at them earlier, that's the mean. That's the population standard deviation. That's the sample standard deviation. Here I have a number of boxes in which to do the same kind of computation. I think the most useful one is the one with the smallest n. Just to play with. Check out the data minus the mean in each case. We've got a negative 11, a 0, and 11. That adds up to 0. We've got a negative 3.5. We've got a negative 0.5. That's negative 4. And here's another positive 4. That sum is 0. It will always be the case that the sum of the data minus the mean for each of your subtractions, each of your differences, will always add up to 0. It'll also be true that your variance will always be a positive because you squared each number to get rid of the negative sign. So everything is positive. That's why when you square it, you want to take the square root to get rid of all that. It's a simplification. I don't think we need to say anything else here. This is weighted mean. You're welcome to play with the table. I'm going to skip it. I'm going on to a new idea, but let's go back to the page we were working on at first. So let's look at the arithmetic a little bit more. We looked at this image comparing a normal number line to a statistical number line. I'd like to talk about that a little more. The two formulas relate X and Z. We'll call that a 0. We'll call this X bar. The middle. We'll say the unit here is 1. That makes this a 1, this a 2, this a 3. We'll call the unit here S for standard deviation. So that makes this X bar plus 1S. And this is another S. So that's 2 S's. And here we have it again. And that makes this one X bar plus 3 S's. I think you're happy with that. I don't know if you're happy with the computation here. X is equal to X bar plus ZS. That sounds like gibberish. X is equal to, whoops, X is equal to X bar plus ZS. This says a number on the x-axis is equal to the mean plus some number of standard deviations from the mean. So let's do an example. Let's let the mean be 10 and the standard deviation equal 5. So if this is 5, that makes this 15. That makes this 5. That makes this 20. And you can see by looking at it that there's your 0. Here's your 1. Here's your 2. Let's see if that makes sense. Here I have some value of x. Right there I have x. Does that value of x equal the mean plus some number of standard deviations? Does that number x equal the mean plus some number of standard deviations? Does that number equal the mean plus, usually you write it with the coefficient in front, some number of standard deviations. Let's figure out what the z is. Just using basic arithmetic, I get a z is equal to 2. Bingo, right there is what it is. So if I took the relationship that says the number x is equal to the mean plus a certain number of standard deviations, then I would get what I needed. I could take that same equation in this term. When I did this, when I had this to start with, I did the arithmetic. Now I'm going to do it algebraically. I'm going to subtract the mean from both sides. That's what I did just above. There it is. There's where I subtracted the mean. Here I get x minus x bar. 20 minus 10 is 10. Divide by s, and I get z is equal to x minus x bar divided by s, which is what this says right there. So it makes sense. The z-score is the difference between the point x you want and the average in terms of the standard deviation. Let's take that again, and instead of solving for z, which we did, here we have it solved for s. So now let's take this one and let's see if we can get the x back. We know it's going to work. Here I have to get rid of the s in the bottom of the fraction. Whoops. Those cancel out. Here I have a zs. Now I want to add the x bar. So those give you a little bit of algebraic practice with x and z. There's more practice here. Here, compute a few values of x and z. These you can do mentally if you wish. Here's the formula. To compute z, enter the value of x bar, the mean, and the standard deviation, and then complete the computation. The x score, let's make it 4. And let's make the mean -2. And let's make the standard deviation 0.2, 0.5. All right, so I have, let's copy the numbers. Here's our example. We'll call it example 2. The x score, whoops, x is 4. X bar, the mean, is -2. The standard deviation is 0.5. Let's do it visually first. -2. Standard deviation is 1/2. I'm going to go up to -1.5. I'm going to go up to -1. I'm going to go up to -1/2. I'm going to go up to 0. I'm going to go up to 1/2. I'm running out of room. -2, -1.5, -1, -1/2, 0, 1/2, 1, 1.5, 2, 2.5, 3, 3.5, 4. That's what I was aiming for. That's my X score. Let's take the formula and see what the Z is. So I'm going to take this formula. Which formula? I want the Z. That's this formula. X is 4. X bar is -2. S is 0.5. What's my Z score? Four minus the -2 is 4 plus 2. 6 divided by 1/2. I get 12. Boy, that's big. Let's see if it works. Subtract the mean from the score. There's the 6. Divide by S. S is right there is S. There's the 12. Let's continue with center and position. Center and spread. Let's continue with center and spread. Again, we're going to spring semester statistics. And this time, instead of going to Monday, the 3rd of February, chapter 2, we're going to Wednesday, the 5th of February, chapter 12. Looks like a slightly odd order of sequence. We go back to chapter 3 and 4 and 5, but these two chapters both deal with center and spread. Monday, as we've seen, talks about one variable statistics, and chapter 12 talks about 2 variable statistics. The PDF of the last page is linked in the comments. The video is linked, and the spreadsheet is linked. So let's open the spreadsheet. I already have mine opened and saved under a different name. We looked at z-scores last time. We changed some of these z-scores. I showed you how to write a function. Here's the function button. I didn't show you in detail. I'll show you now. Excel has a number of functions ready to go. Let's just put a function here. When I put a function, I usually indicate it with a color of some kind. And very often I put a box around it. And then very often I put a label on it. I'm going to call this one average. Average is the arithmetic mean. Add them up, divide by. There is a geometric mean, and that's multiply them and then divide by. But we'll do the arithmetic average. I'm going to sit in the box. In the box, I then go up to the function button. In the function button, because I was using statistics last, the function is sitting right there. It does not need to be, but it's under most frequently used. There's the average, there's the absolute value, correlation, coefficient, standard deviation, factorial, normal distribution. Those are the ones I've used the most, but it's sitting here waiting for me to pick, and I'm going to pick average. And now it's going to ask me for the function's argument, which means what do I want the average of? And I'm going to go over to my test scores. And here are my raw scores, and I'm selecting them. And I press OK. And it computes the average for me. So if I were to change this 6 to a 30, the average would change. If I made it, if I made the 30 a 90, again, the average would change. And because all of this list is required to compute the average, anytime I change any of the numbers, they change. Those are very, very handy things to do. We looked at other functions that I could write. Mean plus a standard deviation, mean plus a quarter standard deviation. Now we're ready to go on to statistics for two distributions considered at the same time. When we do that, we want to consider both x and y, and then x and y jointly. Here's x. Here's y. I can change a value in x. Oh, let's make it really wild. 64, 54. Look at how much that average changed, and the standard deviation changed. And you can look, there's the function defined, and here's this function defined, and here's this function defined. And notice it also states for you the input values, the argument of the function. This one runs in column D from 3 to 12. From 3, that row, to 12, that row. And we need both the mean and the standard deviation of both of the variables. We also need other summations. We need the number of scores. We need the sum of the products. There are the products. There's the sum of the products. We need the sum of the x's. We need the sum of the y's, and so on. I do not know how the formula is derived. I do know how to use it. So that's what we're going to do. We're going to use it. R, there's the correlation coefficient. When I do the computation, I get a negative 0.094. Is that important? What it says is the correlation is only 1% correlated. The X is only 1% correlated to the Y. I think I'd like to draw a scatter plot and show you what a very poor correlation that is. First, I'm going to do a box plot, scatter diagram. And I'm going to do it here. Data. Nope. Insert. I want to insert a picture, and I want it to be a scatter plot. So I went to Insert, and I went to Scatter Plot. And here's the scatter plot picture. I'm going to click on it. I'm going to pick the scatter plot picture, and I'm going to move it over here. Why? Because I like it over there better. Okay, now what I need to do, I need to tell it what scores. Oh, I know what I did wrong. Let's go back. Let's get rid of this. Okay, I'm first going to select all of the scores to be plotted. Here's the X and the Y. So I have 10 different points to be plotted. I've selected them. I'm going to go to Insert. I'm going to go to Scatter Plot. I'm going to say I want this kind of picture, and it gives me the scatter plot, and the numbers are pretty junky looking. Doesn't look very much like a good line. Doesn't look like a good line at all, because look, there's this one way out there. Let's see if we can move this one. This is an X value. That's the wild one we put in. Let's make that an X value of 11. And it does move the scores, so the correlation is higher. Now it's 23%. Let's make it a little higher. Let's try moving one of these 4s down. Let's make that 4 a 6. Brings it down. Let's make this 4 a 3. Brings it down. Nice numbers, not too bad. Not a very high correlation, 19%. Let's look for a moment at what those words mean. Next, we'll consider the correlation coefficient R. Computation is required. We know how to make Excel do the computation for us. Here's the formula for the mean, and here's the range of scores used to compute this mean from C3 to C12. Here's the standard deviation from C3 to C12. That gives us the X mean and standard deviation. The Y mean and standard deviation. Those are the scores we're using. The average in the D column from 3 to 12 gives us those numbers. Other summations are required. We need the sum of the product of X and Y. We need the sum of the X's. We need the sum of the Y's. All that can be computed and is computed for you to use on your spreadsheet. And when we do the computation, we get an R, a correlation coefficient of 0.44. Before I speak in words, I'd like you to see the scatter plot of it, and then we'll maybe do the regression line, and then we'll talk about it in words. Here's what you have to do a scatter plot. First, select the 10 ordered pairs, just like that. Then use insert, then the scatter plot picture. So up here is insert, and then the scatter plot picture. And that's the scatter plot. Then place the plot where you desire it. I don't want it there. I want it here. And I think just to make it look prettier, I'm gonna set it off with the color so you can see the chart better. I'm just gonna move this a bit. Okay, doesn't look like it's has a high correlation. The correlation, the percent of R squared expressed as a percent is 19%. That's not very tight. That's not very high. Let's see if we can make it a little higher, a little closer. Perhaps we'll move this X value, looks like it's about 11. Here we have an X value of 11. Let's change that to an 8. And that'll move it over a little bit. Oh, that's a little better. Let's make it go up a little higher. So now it's at 8. We'll make it go up not to 6, but let's make it go up to 8 or even to 10. Now that's a little tighter even yet. Now it's at 49%. And we'll pull this one down. It's at 3, make it down to 8. Do I have a 3? Yeah, let's try it at 8. Let's see how high we can get that score. We're getting there, 57%. That's still just not even 2/3. So we need to do a few things. We need to look at words and we need to look at numbers. Let's look at the numbers first. The numbers are provided on the web page. And here's the numbers that the professional organizations are using. Correlation coefficient. If you are in, let's go to medicine first. Now let's go to politics. Politics. If you have +1 correlation, it's right on the money. No spread at all. You get a line with a slope of 1 or a slope of -1. A slope of 1 would mean as X increases, Y increases, exactly the same way. If it were a negative, as X increases, Y decreases, exactly the same tightness. That's in politics. It's a perfect correlation no matter who looks at it. If the correlation is 0, there's no correlation. That means anything's floating all over the place. Now we look at the shades of gray in between. And if you are paying attention to politics, if you listen to the presidential race, Quinnipiac was quoted so often. They're a very, very reputable university. strong statistics department. Good place to go for a 4-year degree in statistics. It would be great to have that background. So, according to their standard, to be a very strong correlation, you have to be 0.7 or above for an R, for correlation coefficient, or 0.7 and below. That's very strong. If you're between 0.4 and 0.7, it's strong, then moderate, then weak, then negligible. Negligible would be 0.1 or what, a tenth. That's if you're talking politics. If you're talking psychology, you have strong correlation, moderate, weak, and zero. If you're talking about medicine, a very strong correlation would be 0.8 and above. I think you get the idea. I think this is a value. It's there for your reference on the website. Now we go to words, not just a number and a word. And the word, the meanings we had two features to it, or one or two. We could describe it in one word, or we could describe it with 2 words. Actually, each of them was 2 words. It's either a positive or a negative, and it's a strength. So let's look at the words that I suggest. Not me personally, statisticians. Use the correlation coefficient to interpret the regression estimates. The regression estimate is that percent of R squared. If your R is 0.55, the correlation coefficient is 0.55. That's because R is correlation coefficient. This indicates a strength and a sign, negative or positive, and the strength. Let's go back and look at our scores again. Maybe I should put that in on this page also. Let's see if I can do that. Go back to the web page and make this smaller. Okay, now you have a whole paragraph in addition to just a few words. So if R squared is 0.55 squared, then 55.55 squared is 0.3025. Call it 0.30, that's 30%. We can say that about 30% of the variation in Y can be explained by the linear relationship with X. And about 70% cannot be explained by the linear relationship with X. If the linear is not a good fit, you could try an exponential or a log. And I'm not going through those today. Those you can see on the calculator. That would be, your Your J curve would be an exponential. But you now have words, brief words, and more significant words. Okay, I think we've about done it with regression lines, except did we get the scatter plot? No, we did not through the regression line. I think I have another one for it. And I want to go with a regression line, beginning with the scatter plot and just going through the instructions and showing you what's going on in picture form. So let's go back to the web page and let's call this up because I can make a bigger copy of it. And this you can also download. Least squares is another word for the regression line. It's also called line of best fit. Y hat, the median, is, think of y equals mx plus b when you were a kid in Algebra 1, or y equals a plus bx as your calculator would show it. That's the error. That's the regression line. Here's the scatter plot. R is the correlation coefficient. S, the standard deviation of x, is the x values. The standard deviation of the y's, this is the y values. Y over x is slope. So the slope of the regression line is the correlation coefficient times that standard deviation of y over the standard deviation of x. Where the errors are all added up and averaged. There's the errors. They're all added up. The sum of the squares errors. Go back to the spreadsheet. Let's now go through making a scatter plot and then adding the trend line, the line of least squares, the regression line. Okay, I'm going to put it over here. I'm going to make it blue so it'll fit. I'm following these instructions. Draw a scatter plot first. You have to select your ordered pairs. Then you use insert and then scatter plot. Here's insert. There's your scatter plot. That's the kind I want. I'm going to drag it over here. I'm going to make it a little bit smaller. Okay. It's always a good idea to save everything so you don't lose it. So that's what I'm going to do. File, save. Okay, it did that. Then add a trend line. Here's the instructions right from Excel. Add a trend line to the chart. Select the chart. Then select the plus sign to the top right of the chart. Then select trend line. So it's a three-step process. I'm going to select the chart. There's the plus sign. Down here is trend line. And there's the trend. Now, what I also put into the spreadsheet is the computation of the A and the B in the regression line. And I can get out of that, and I can save it again. Now, what I can then do is use the trend line to predict. Put an X value in the orange box to compute, and I spelled compute wrong. Put an X value in the orange box to compute. That's all you have to do to change it. To compute the matching Y hat value. So I'm going to put, let's put a 2 here. What that'll do is it'll tell me what the value on the regression line 2 matches with. I'm going to put the 2 in. Okay, I got the 2 in there, and I don't see anything here because I haven't told it I wanted it there yet. So now what I have to do, and I did not put this in the instructions. Yeah, here we go. Then add the point X, Y hat to the scatter plot. And you do that by, again, selecting the chart, right-click the mouse, select the data, and enter the orange X and its Y hat. So I'm going to right-click the mouse, and I want to select data. Bingo. Then I'm going to select another series, and I'm going to add, I think I need a name for it. And the X value is here, and the Y value is here. And there's the chart. There's the value sitting right there. Do I need to do that again? Maybe one more would help. So I'm going to undo it. How do you undo? You go Control Z, and it gets rid of it. Okay, so let's put another value in here. Maybe we'll put in a 5. Let's see how close we can get to right there. It should give it to us right off the bat. So I'm going to put a 5 here. And my Y value changes. And now I want to stick that in the graph. Select the chart. Then right-click the mouse. Then select data. Then I need to call it something new. No, I think add first, and then call it something new. And then add the X value there. And go to here and put the Y value there. Click OK. There we go. There's the value of 5 right on.